So welcome everybody again to this series of seminars by Quantum Spain. We're glad to see many of you are you have some of you have a high fidelity, and today we're going to speak about high fidelity. So it's a pleasure to have today Jakub Mrożek. I hope I pronounced it correctly. Yeah, from IQM. So as soon as I saw this paper announcing above 99% fidelity in single, two-qubit gates and readout altogether, we sent a request to IQM to have someone reporting on this paper, and Jakub has agreed, and we're very thankful to him. Jakub is Polish and studied in London physics, but then went to he also did his master in the University College, and then he did a PhD in condensed matter and materials in Oxford, and he's a quantum engineer in IQM since 2022, working on the QPU control team, calibration and error amplification, and all that. So Jakub will tell you today everything you wanted to know about calibrating a 99% fidelity CZ gate on a superconducting quantum processor. So as usual, if you have an urgent question, you can raise your hand and we will unmute you. Otherwise, we will leave the questions for the end of the seminar. And Jakub, the floor is yours. Thanks.
Thank you very much, Javier, for having me. And yes, we had this paper. Today, I would like to focus on the two-qubit gate specifically and the techniques that we used to calibrate it to such a high fidelity and to essentially measure all of the coherent errors that the gate has. There is more content in the paper. That was just mostly the part that I was working on. So this is what this talk is going to be about, and we'll try to cover everything from the qubit architecture that IQM uses to some basic error amplification to the PALEA, which is the protocol that we have introduced in the paper. And then we also show some kind of optimization that we have done over the two-qubit gate to bring it up to the high fidelity. So starting with the qubit architecture, IQM uses superconducting transmon qubits, which are at this point very well established platform for quantum computing. What a transmon qubit is essentially a loop of a superconductor which has an added anharmonic element, which is a Josephson junction. And what that does is, starting from a quantum harmonic oscillator, by adding this anharmonicity, you're able to effectively isolate the computational subspace in the first two levels, because the transition between 1 and 2 has a smaller frequency by this factor alpha than the 0, 1. So we can use those two levels as a qubit. However, we also use the second excited state for gates, as I will explain in this presentation. So the single qubit gates, we use just microwaves, where on the chip there is a antenna that is capacitively coupled to the qubit, which is this blue part. So those two diagrams correspond to each other. This is the false picture of a chip, and this is the RC diagram. Shows everything. So I have a capacitively coupled drive and inductively coupled flux component. So here you will have a pulse coming in that you can use to change the qubit frequency instantaneously. And how it works is that you have this loop of two Josephson junctions, which is this anharmonic component in the circuit, and the amount of flux that goes through this loop changes the transition energy between the 0 and 1. So, for example, here when you sweep the amount of voltage you apply to this antenna, the amount of magnetic flux going through the loop changes, and that changes the transition energy. And that is how we change the qubit frequency, but also how we implement the gates. With our architecture, we use something called a tunable coupler. A tunable coupler is also a qubit, is also a transmon, but it has a different shape, and it's optimized for different purpose. So here in the middle, we have the coupler. This is how it looks. You can see it's very different than the two qubits, but both of those things are transmons. They are just optimized differently. And the coupler is needed to, first of all, turn off the ZZ coupling, but also to implement two-qubit gates. So the idea is that when you are not doing the two-qubit gate, you change the coupler frequency, you put it below the qubits at the point where the total ZZ interaction between the two is 0. And that allows you to treat each qubit as a separate element. During the gate, you would move the coupler up by sending a flux pulse, and that changes the frequency of the coupler and also turns on the ZZ interaction, which enables you to perform a gate. Simultaneously, we would add a qubit flux pulse, tuning one of the qubits down so that the two qubits end up and there's very specific resonance. So what we see here is that this is a qubit-coupler qubit. The colors correspond to this picture above, and we have this 200-101 resonance. And what happens there is we turn the coupling on and we go to this regime for just short enough time so that you generate a 2 pi rotation on this in the subspace between those two states, but the other 3 states are not doing anything interesting. So you essentially go from 1-1 to 2-0 back to 1-1, but with the conditional with the phase shift only on this state, which effectively implements a CC gate. So this is how the gate is done, and basically every chip that has this architecture, not only ours, but I wanted to introduce it for the people who don't know. We also use some Slepian pulses to limit the leakage to the coupler element so that it stays in the 0 state after the gate. So in such a gate, we have several things to calibrate because we need to calibrate the gate. First thing is, of course, the ZZ rotation angle that the gate is implementing. We want it to be pi. We want the actual phase shift to be -1. But we also need the ZI and IZ rotation angles, which is the phase that each qubit acquires during the gate, independent of the other qubit. That has to do with the fact that we are changing the qubit frequency momentarily. We're putting some coupling on, and there's many effects that this can come from. But this is just done with virtual Z rotations on the driveline. So we actually are not fixing those things. We just pretend that we fixed them, but it is good enough. However, one additional thing that we need to fix is that this coherent leakage from 1-1 to this 2-0 state is also 0. Because if you rotate around, then you might leave a little bit of the amplitude in this 2-0 state, and that causes leakage to the higher excited state, which is quite bad. Nobody likes leakage. But it is part of the gate that this thing is the state is occupied, and we just need to empty it effectively to get a good gate. Okay, and also leakage to the coupler. Okay, before we start calibrating the gate, we do quite extensive characterization of the QPU. So we measure all of the frequencies of all of the components versus all the control parameters, right? So because we apply this voltage to change the frequency of the qubit and the coupler, we need to know what is the actual function relationship between those two things. And we model the system with this Hamiltonian that contains 3 elements. The lambda here goes from 1 and 2, so we have the 2-qubit term, and also the coupler. You have the single qubit terms, and you have the couplings. In our architecture, specifically, the couplings are the coupling between one qubit and the coupler is negative, and the other is positive. This is quite important for people who are interested in that. And what we'll typically do is we just measure the avoided crossing and try to try to obtain the values of all of the parameters here as a function of the voltage. So the couplings and the frequencies of the qubit, and also the unharmonicity, which is the difference between the 0 and 1, 1, 2 transition, just to remind that. Okay. The way we calibrate the gate is we start from something. So one the naive way of doing this would be to measure what happens when you use gates of different pulse shapes. So you can change the coupler pulse width and also the maximum coupler frequency during the gate, and you obtain this sort of chevron pattern here. Alternatively, you can try changing the frequency of the qubit pulse and the coupler pulse, and then you obtain a pattern like this. And looking through this is quite expensive. So what we prefer to do is separate the variables and convert it to 1D problem. So after just measuring this, which is just the probability of a population return, so we are concentrating on making the leakage to this 0-2 state 0. We know that the gate must be somewhere on this line. So when we measure the conditional phase or the ZZ interaction, we just would just measure along this line. However, we can go even better, which is we just guess what pulse width or the qubit frequency we would need from the model. And for the coupler pulse, we typically use the sum of inverses of the couplings that we have measured, which is a good initial guess. It obviously depends on many other things, but it's a good beginning. So you can see that already from just this one point, we are able to get quite close to the final gate, which is given by this X. Okay, so what this means is that we can start from error amplification experiments right away. We don't really have to measure to perform the experiments that are not kind of an error amplification experiments. And for conditional phase, we use this protocol that is designed by Google, which is called MEADD, which is a very good protocol, where you would prepare the two qubits with the pi over 2 on one and the X gate on the other qubit, effectively bringing it to like a 1, 0 plus 1, 1 over root 2 state. And then you would repeat the sequence of a CZ gate or a CZ gate candidate, and followed by 2 X gates on both, or 2 pi pulses on both qubits. And so what this does is it removes the individual phases from the experiment. So if the CZ gate is not only introducing conditional phase, but also unconditional phases, or just a phase rotation of like Zi or Iz, those are refocused by this dynamical decoupling. And this protocol then allows much faster measurement of the ZZ angle. So for example, here we measure until like 70 gates, and we know that for some value of qubit frequency, we cross 0, and this is where we want to be, because we assume we are quite close. So by doing 4 of those, we would expect the overall phase shift to be 0 if the CZ is implementing a phase pi. We wanted to so this is an explanation of how that works in detail in terms of the RZ phases. So if you assume that the CZ is doing some amount of set rotations on each qubit, followed by like a conditional phase, then that we can see that adding 2 X gates and then doing the thing again converts this to an operation that just introduces the ZZ or a conditional phase error. So for that reason, we don't have to worry about those single qubit rotations. We will fix them in the end after we have calibrated the gate with virtual Z rotations. Okay, so that was the first part about like the basic calibration, and now we can go to this more advanced phase matching description. So if you think about a general, if you think about repeating like an imperfect single qubit gate, then an imperfect single qubit gate implements some rotation by x by an angle pi over delta, where delta is some error. But if you repeat 2n of those gates next to each other, then you would cancel this pi by doing 2 of them, and you would amplify this delta. So we're doing many gates. You can see that this bang protocol is just Rabi oscillation, is just sort of a discrete version of the Rabi oscillation, where you, instead of looking at the oscillation in time, and you see the oscillation, the number of gates that you perform. So we want to use something like this for error amplification. An important point here is that the frame of reference is quite important for amplifying this leakage error that we haven't yet solved. So for example, if you look at single qubit gates, that if you move the gate forward but you keep it at the same frequency, in order to make to keep the gate doing the same thing, you need to advance its phase with the same rate as the frequency is advancing its phase. If you don't do it, then the pulse will look the same, but it will do something different. So sometimes we have a gate that does the X rotation, but it also but it might be a bit more general. So we are focused on optimizing the angle for the X rotation or the Y rotation, but we also have some Z rotation. And as I explained before, we are going to do Z compensation at the end, which means that we don't really necessarily want to treat the Z error as an error at this stage. So you would just want to focus on the Y error. So what we can do is you can decompose this whatever this other gate is doing into the Euler angle decomposition with Z, Y, Z angles, so some phi, theta, and lambda, and then we say that the lambda and theta we don't care about, and we only care about the theta because that's what our error is that we have to fix by changing the some kind of physical parameters of the pulse. So what we can do is we can move the gate in time effectively until it's matching this carrier, and then by doing that, we again are doing another Y rotation. The free Hamiltonian then would fix the Z rotation for us. So we want the free Hamiltonian to act for the sometime t such that its action is equivalent to a Z rotation of 2 pi minus lambda minus phi. And when it does it, we can sort of interleave this u, which is our gate, the unitary that represents our imperfect gate, times this free Hamiltonian. So we basically do unitary Hamiltonian free evolution, unitary Hamiltonian free evolution, and when you do it n times, we end up with this rotation by an axis y of n theta that amplifies our error. The other thing you can do is you can just somehow introduce a real Z rotation that acts in the same way, effectively changing the phase of the carrier or some kind of reference. And what this does is essentially the same thing. Now we're just applying this RZ minus phi minus lambda n times the u, and that gives us the n theta. It could be some kind of virtual Z, it could be a flux pulse, or some other way of implementing the real Z rotation. So this has been published again by Google, and they call it Floquet calibration. The main idea is essentially that you can always perform the add this Z rotation to amplify the error that you want. So let's look at how it works for this 1102 exchange that we want to get rid of, right? Just to remind, the 02 state is always entered by our like during the gate, but we want the state to fully return to 11. So what we can do is you can say that this unitary that our CZ gate is currently implementing, it is imperfect. It doesn't do exactly what we want to do for now, but at least we assume that it doesn't leave this subspace. So it's always staying in this 1102. If we prepare 1-1, then we will get some superposition of 1102 and the same for 02. So then this is essentially a single qubit unitary again that we can write like this. And what we can do is we can do this experiment where we prepare the 1-1 state first, and then we do the CZ, or like our version of the CZ that they're doing at the moment, followed by some kind of real Z rotation. So here what I'm doing is I'm doing a pi pulse, and then I'm doing another pi pulse, but of a different phase. So that implements the Z rotation of angle 2 phi on this 1 qubit, and that is enough. So when you do this, what happens is that if you have your gate is pretty good already, you will see that for most of those Z angles, you will see almost nothing happening. We prepared the 1-1 state, and now we're looking at counts of 1-1 in our experiment, and you see that most of the time you have like 100% of counts of 1-1 in this graph. But for some angles, like 2.4, we will see that there's something interesting happening. There's an oscillation. And we can fit that oscillation with some whatever sinusoidal function, and to uncover this angle per gate, in this case 0.2. So this angle per gate is this theta that we are caring about. This is the y angle rotation, and our error is basically just this angle, because we can always fix the z rotation. So we don't really care about the z rotation. We are only caring about this theta, and now we can measure what it is. So we can very precisely benchmark the error in our gate. And this actually can be done for any the process that involves two states, however exotic they might be. You just need to have a way to implement the Z rotation between the two states, and then after preparing the state from the subspace, you just check different angles, and for the one that you have the biggest effect, just take that as your error. One particular application of this is measuring the leakage to the coupler, which we've done in the paper to measure this particular error. So now the zero and the red state in the middle is the coupler state. The lower qubit leaks to the coupler coherently because the coupler comes very close to it during the gate. And so if you just write our gate now in this subspace, then it again looks like some kind of Euler decomposition that has three angles. For this experiment, because we don't have the readout on the coupler, we want to prove that this is actually the coupler that we are measuring. So we just interleave this version with the free Hamiltonian evolution when we add some time during which the system evolves by the difference of frequencies between the coupler and the qubit. So what we see is that if you look at the counts of the 0-2, but after preparing 1-1, you will see this big feature that corresponds to our big process of 1-1-0-2 exchange. But if you look at the population of 0-1, then we see those diagonal lines where actually it is 0-1, but we cannot measure the coupler. So really what high population there means is that this state 0-1-1 is populated. And then we can again find the peak in this data that corresponds to the amplitude or the pulse that we are actually sending. And while we are here at this peak, we then change the number of vary the number of gates, and we obtain some kind of oscillation. Then we can again fit to extract this angle that tells us how much coherent leakage to the coupler we have, so we can quantify how big of an error that is. And we confirmed that this is the coupler by essentially Fourier transforming this data and showing that it corresponds to the frequency difference between the qubit and the coupler, so the frequency difference between those two states, which is what we expect. Here's a bit of a bonus. If you use it on a chip with more qubits, then you might see a different effect, which is that if with 5 qubits on the chip, prepare the 1-1 state on the qubits 3 and 5, and perform the CZ gate there, you will see that you can coherently amplify the leakage to spectators, and it appears as those features in the data. Right. So yeah, we can mitigate that maybe. And if someone has access to one of those vendors, then they use the same CZ gates, and this experiment is quite easy to do. So we can see if there's some kind of error of this kind without having access to any pulse level system, which actually we also offer. Someone wants to screenshot that. We also offer 33 credits on our system. So if someone wants to even check out how well we are doing, it is available. Okay, the next part is what we have actually implemented. What is the new way of calibrating this 1102, which comes from the observation that having this theta angle being large is good. What this means is that let's just say that this theta is very small, and we add some random z angle which we don't know what it is. We sweep that angle, and here 0. I'm using 0 because it is general. But of course, in our case, 0 would be 1, 1, and 1 would be 0, 2. So we see that after just calculating what this expectation value would be, we will see that we only have quite large population on the angle that precisely matches the angle that is part of the gate, which in each case means that this z rotation is 0. But everywhere else we have very low coherence, a very low signal. And what basically this comes from is that when we start from 0, this is mostly a z rotation. So in visualizing on the Bloch sphere, only for some values of the z angle, we actually see something that goes all the way to 1. But if we have the same angle, theta, but instead of theta, we have pi minus the same theta, then actually what we see is that the rotation is now mostly dominated by the y part. And we see big signal. We have a very large signal everywhere, and this can be shown on this Bloch sphere, visualized here. So what we essentially want is that we want to convert this theta from being small to being large. Yeah, so this is motivated by calculating the eigenvalues of this rotation and the eigenvectors. Okay, so how to do that in practice? It's not easy because we have the 1120 is a or 02 is a any state that is a superposition of those two is entangled, and the only way we can have an entangled state is using the CZ gate, so it's not really possible. But what you can do instead is we can convert this theta angle to be a pi minus theta by applying X gates, or in this particular case, we need to apply an 1-2 gate to the higher frequency qubit that flips between the 1 and 2 state, and at the same time we flip between 1 and 0 on the lower qubit. So we start from 1, 1, the CZ gate is doing something, then we flip the 1, 1 to 0, 2, doing something again, we flip to 0 to 1, 1, and so on. We can show that this phase depends on the phases of both of those pulses, specifically on their difference. So in the end, what we do as well is we average this phase. So actually each shot of this experiment has a different phase, and as a result we see the average signal, and the average signal looks like this. So we see that for the correct coupler amplitude, which is about 0.45 here, we see that the signal never decays, but for any other incorrect one, the signal decays quite quickly and then oscillates a little bit. Yes. In our system, we actually have an electronics limitation, which forces us to average this phase. We cannot actually control the difference of the microwave phase between those two channels, but you might want to do it anyway, even if you can control it. We can show that this complicated model is fitting this data. So analytically, it's quite a complicated integral, but you can show this if you want. Also for small thetas, this is a Bessel function. And so we can fit this directly to extract the theta. Or the other thing you can do, okay, I'll actually have it later. So we can, for now, we can fit this to extract a number theta. And another thing that you could do is you can measure the swap error in the gate, which is this kind of error where you have some off-resonant oscillation between the state 1, 0 and 0, 1. So this is how we measure the swap error in our gate. This is the same pull sequence that is in this MEADD paper, but we're also averaging the phase on top of that. And we can measure our swap error in our chip to be very low. And also, if you want to optimize the pulse width to get rid of it completely, then that is also possible. It turns out that the swap error in our chip is so small that it is actually not a good idea to optimize for it, because there's other kinds of coherent errors that generally make the pulse width not like optimizing for swap error not the best, because then you have other errors on top of that, and the total error is higher. This is just a consequence of the fact that it's very low. So we can use the same logic to measure this, and again fit the same model. Okay, the other thing that this PALEA protocol is doing is it gets rid of the coupler leakage. So what happens to the coupler leakage in PALEA? So we would like to think that it maybe just averages to a small number, but actually what is happening is that if you have some coupler leakage, so we have population in this 0, 1, 1 state, after applying this layer of EFX, it transfers to this state, which has 4 excitations, and that state sort of explodes to some other different states, because effectively from the perspective of the coupler, we are pumping energy in the system every cycle. But we can perform some simulations that show that compared to the Floquet calibration method, we actually see a lot less population in the coupler, which is good because we actually don't want to see it. We are measuring something different. Okay, I will skip like a very long explanation of this. The main mechanism of PALEA, which is why it can be used in other systems as well, is that again, you sort of follow the same logic as the Floquet calibration. You express any gate as this unitary that has Z, Y, and Z, and you prepare one of the states A and B, and then you interleave between each U some sort of swapping with local operations. So the two levels, two states A and B, have to be such that you can perform local operations to go from A to B, but presumably mixing or going into a superposition state requires some kind of entangling operation, which you don't have. And then if you average the phase of those local operations, that you get this model. So we applied it to this 0, 1, like with 1, 1, 0, 2 operation, but you can also apply it to other. As long as this behaves this way, then it will work. The other thing that you can do is we can notice is that this model that it fits the data actually is only higher than 0.7 roughly on this first period. So if you look at the oscillation in terms of the number of gates, then we'll see that only for the first 5 gates in this particular case, the signal is higher than 0.7. So which means the probability of measuring 1, 1 again is only higher than 0.7 here. So then what it means is that if you do 100 gates and you still measure above 0.7, this means that you are necessarily in the global minimum and not the local minimum, because the local minimum or local maximum, local optimum will be here, and you will see a much lower signal there. And this is a consequence of this phase averaging. So then PALEA can be used without a fit or varying the number of cycles. You essentially just measure, for example, at 8 gates, and you vary some kind of parameters of your gate in any sort of optimization algorithm that you like CMA or Nelder-Mead or something more complicated. And here I'm showing some experimental data that illustrate the point, which is that the phase averaging guarantees this global minimum in the middle is always smaller than any local minimum. So we are not able to you're not going to be caught in the local minimum as long as you just tell your optimization algorithm that it needs to look for something that is close to 0, and not like it shouldn't be happy with anything that is like, for example, 0.5. Okay. Right. So we've covered the PALEA protocol, and I want to also show our graph-based calibration framework, which we use to calibrate this gate. How it works is not necessarily very important, but in short, in order to calibrate this thing fast, we are not only running the experiments in order, because you need to do several iterations of the calibrating the ZZ angle and the calibrating the 1102 exchange. But we also have these fallbacks, which mean that if something goes wrong, that we will do the 2D big experiment to find the gate again. And this way we perform the time-consuming calibration only if this mostly risky path fails. And that is important because we are able to quickly optimize for any given set of parameters, perform all of the experiments precisely, and then extract the fidelity of the gate. And because we are able to do it very fast, we can check a lot of different combinations of parameters and basically arrive at the best parameters before our system again somehow drifts, and we have to recalibrate even more. So for this gate that we have in the paper, we first performed this kind of optimization where each point is this whole run of the graph over several durations of qubit frax pulse. That is for how long the qubit the frequency is shifted. And then we followed that after finding the best parameters with the lowest error, about 27 here. We have then performed it for the coupler, where the lowest error is around here. And you can see that the swap error that we also measure, actually in the minimum is slightly higher, but the overall fidelity is here the highest, so the error is the lowest because of other coherent effects that are also involved in the gate. But because we can do it fast, we are also able to do basically more points. And finally, to show that our fidelity is very high, we perform this iterated randomized benchmarking, which is the same thing as interleaved randomized benchmarking, but we will interleave a sequence of n gates instead of just one. And what this helps us to do is that we can quickly see if there's a non-Markovian error and accumulate incoherent errors. So by this point, we should have measured or eliminated most of the coherent errors, because with coherent errors, this actually doesn't work very well. But with incoherent and incoherent errors, it does work very well. And then the non-Markovian errors completely break the model, so we can very quickly see that we have them. This also serves as a confirmation that their fidelity stays very, very good for extended period of time. Here we've done it over 40 hours. And the average fidelity over this time has been 99.93. But the best point is a bit higher. Of course, this is the data from the best point. So we have this 99.93 average over 40 hours. So in the total system, I haven't talked about our single qubit gates or readout at all, because this is possibly another talk. But in this system, we have everything is quite good. The single qubit square root of x error is about 1.6 to the -4 with very low leakage. We have readout fidelity about 5.5 10 to -4, which is also very good. And obviously the CZ error is also very low. With the incoherent contribution that is measured by simply looking at the fidelity of the identity or just doing nothing for the same amount of time, we have some coupler leakage that we measure with this experiment I mentioned earlier. We have leakage to the second excited state that remains. It's mostly due to the phasing, why we still have it. and then there's the swap error, which we can measure with the PALEA protocol. Okay, so to sum up, everything is Rabi experiment in terms of error amplification. You just need to find it. You can use Floquet benchmarking for visualizing those exchange error modes. But PALEA is the best tool for calibration optimization of this kind of errors in the gate. We have very higher fidelities in CZ gates, but in the same device, you still have very good single qubit and readout fidelities. So yes, thank you very much, and that was
Okay. Yeah, thank you very much for the talk. So I must say it was a little bit technical for me, but I'm sure there will be people in the audience that appreciated the details. So I just open the time for questions. Don't be shy and take your opportunity to ask details.
Show is that we haven't made any we haven't made compromises in terms of making a device that is very specifically tuned to or designed for the two-qubit gate being good. We also can have good other operations, but in terms of the order in which we optimize those things, the parking on the chip or the frequencies of the qubits during the idling, which you can change by applying the different voltage, DC voltage to the flux lines, that impacts the fidelity of the two-qubit gate. So we would actually first do the two-qubit gate, and then which involves maybe changing the frequencies of the qubit, and then at that point where we have gotten the two-qubit gate, we calibrate the single qubit and the readout, which will first do the single qubit and then the readout, because the readout needs the single qubit to find out what is the assignment probability of the one state we need to prepare it. So this is the order. First we do the CZ gate, then the single qubit, and then readout at the end.
Mm-hmm. And the fidelities in the readout are what are they in the?
So we have an average error in the readout is 5.5 10 to minus 4. So the fidelity is 99.95 as well, 94.
Uh-huh. This includes intermediate measurements, or is
No,
this
this is just assignment fidelity.
I see.
So also in this paper we are showing the QNDness, which is the probability that the readout does not flip the Z eigenstate, that is quite high, but of course I haven't included this in this presentation.
Yeah. Any other comment or question? I was also curious about this coupler leakage. It's just that you happen to find that it was small by simulating, or you really understand why it's small?
So we do understand why it's small. We are using this specific pulse shape, which is called the Slepian pulse shape, and that Slepian pulse shape is able to limit the leakage to the coupler to be quite low. It's not perfect, and generally how it works is that you need to know all of the Hamiltonian parameters. So you need to know all of the couplings between the qubit and the coupler, and the qubits direct coupling, and then you optimize that numerically for the pulse shape, which you use to limit the coupler leakage. And this experiment that I'm showing here in this slide takes a very long time to perform. So this is used as a benchmark. We are not able to optimize over this. It just takes too much time. You need to know both this precise time and all of these other things. So it's not really good to optimize over this. But we use the numerical optimization of the pulse shape to get the coupler leakage low.
Yeah.
And essentially, if you make the gate too short, then this numerical optimization does not work anymore. And we are kind of pushing it as short as possible to limit this leakage.
I see a question. Guillermo, I think, let me see if, you're unmuted now.
Can you hear me?
Yeah.
Yes.
Okay, perfect. I have a question which is a bit, let's say, more operational. And I mean, IQM machines that have computers with like 50 qubits and with a lot of connectivity. It's like a square grid, no?
Right.
And how long does it take to calibrate all of the possible CZ gates? Like if you can comment on this, because it must take a lot of time or not, or maybe you can parallelize a lot of things in the grid or something like that.
So I actually have another presentation that deals with that, and
Okay.
but I can tell you, we can calibrate any chip of any size that we currently have, which is 20 or 50, in about 10 minutes. The 2-qubit gates, the whole chip. Of course, in order to do that, you need to first know all of those Hamiltonian parameters, because this is essentially what we do in this initial part that I was showing at the beginning, which is that you would ideally try to find the good gate point in this graph somewhere. So you have the population exchange between 1, 1, 0, 2, and you have the conditional phase, and you need to find a point where you have both are good. And what we are able to do is we are able to guess through the Hamiltonian parameters where this point is. So once we are able to do that, then we can do it for simultaneous with all of the pairs on the chip. And then we calibrate in 4 groups. So each qubit is connected to 4 other qubits, so we can pick sort of a cardinal direction and do 4 layers of gate calibration. And the total time for calibration and benchmarking of all of the gates takes about 11 minutes, including the randomized benchmarking. Or if you don't want to do that, then it's about 8. It's the randomized benchmarking is actually quite a bigger time. Of course, that will give you a calibration or recalibration. So sometimes for this kind of fidelity, you need to spend a bit more time sort of manually adjusting it, but we can get to pretty high numbers without that.
Oh, nice. Can I have another question? It's also related
Yes,
to the
go ahead.
because there's also the issue of, I mean, you can calibrate the gates very, very nicely. You can have the parameter very well tuned, but at some point it will, drift away from that calibration, and it will depend on a lot of things. It will depend on even in the wherever the computer, the quantum computer is placed. But I guess you kind of, because of you had a calibration before, you had an idea of the parameters or how far can have this drift. So do you have this take this into account of, okay, this was the last calibration, so it should be close to this to accelerate the process, or you have to go from the beginning, let's say, no, from, oh, no, let's do it like it's just the first time. Also that, and if this merits like triggering the calibrations when you know that something is wrong or something like that, or you do it like quickly or whatever.
So typically on the production systems that are on the cloud, for example, their calibration is done every day, once a day. It is typically enough to do it like that. And in terms of the actual process, we do start the calibration. So this is this idea of this graph-based calibration with fallbacks.
Yeah.
So we start from assuming that it's close. And then we basically, during the calibration, have checks. And if the check tells us, oh, actually, it's not close, then we revert to a more expensive experiment that takes a bit further. And this works very robustly because, for example, if you only have 1 or 2 gates that are drifted, you have 4 layers. So 2 of the layers calibrate very fast, and the other 2 take a bit more time.
I see that. Okay, thanks a lot.
Juan Esterijo. Let's see. Alberto, can you unmute you?
Yes, can you hear me?
We can hear you, yeah.
Perfect. I would like to ask if flux distortion is an issue, and if so, how do you measure and correct for it?
Okay, a lot of questions about things that are not in this presentation, but I will answer because I know. So we have 2 methods of measuring the flux pulse distortions. We have the long experiment where we measure when we use to find these long distortions, which we then correct with the infinite intermediate response filter. And then we have another experiment for the short time distortions where we correct them with the FIR filter. And the first experiment is essentially we play a flux pulse, and then you wait some time, and then you perform a Ramsey sequence. So pi over 2, some delay, and pi over 2. And then we would move this. So this is a very standard experiment. We move this Ramsey sequence away from the flux pulse and And we have some modeling done that kind of predicts what kind of phase you can measure in this experiment. Phase shift you can measure based on the distance from the flux pulse. And based on that, we can calibrate those long time distortion, long flux distortions. And then with the other experiment, we use the Delft Delft cryoscope, so-called. There's a paper from Delft from 10 years ago, when you would do the flux pulse in between the 2 pulses, and essentially just change the duration of the flux pulse to see how the phase changes at the sort of the rising edge of the pulse, which you then can invert and correct with an FIR filter. So we do all of these things, and those things are part of the graph-based calibration. So they are typically done automatically. And again, this part is not included in the 10 minutes that I mentioned, and this is because we find that those filter parameters, they actually are not only stable for a very long time for the same chip, but they're also stable if you even change the chip. So you have the same fridge, same instrumentation, and you exchange just the QPU, and they typically don't even have to change those filters there. For that reason, even though it takes quite a time to calibrate them, we don't include this time into this 10 minutes, because we do it for a given fridge every 6 months. So that is just not fair to include it in the time. But it takes overnight to measure the whole chip like this, if you need to do it.
That's amazing. Thank you.
Okay. I have a last curiosity. So you mentioned you have to get the hold of these complicated Hamiltonians. No, that so you do some kind of Hamiltonian learning or machine learning. How is the process to learn all these Hamiltonians? Is this easy?
So in this particular case, what we do is we just this is the model Hamiltonian that we assume that our system is. And we would simply perform experiments like changing the coupler frequency and looking at the avoided crossing to measure the couplings. For the G12, we would measure the ZZ coupling versus coupling frequency. So we just look at what is the conditional phase on the qubits when they idle, when the coupler is somewhere. And obviously the frequency and anharmonicity you can measure with microwaves. So the whole problem is to measure this across the different range of control parameters.
Okay, I think it was very fruitful, and I want to thank Jakub for his time, for his expertise, and all you for attending the seminar. And we reconvene in 2 weeks back here again. Well, have a nice time, everybody. Goodbye, Jakub. Goodbye, everybody.
Thank you for the invitation. Have a good day.